All right, so one thing I wanted to show you before we get going. So I added some stuff, kind of rearranged things on Canvas. I think this is what it should look like for you. So you kind of notice there's categories that don't have kind of any weighting here. And I'll explain that in just a second. But what I've done is I've identified kind of your lowest and highest exam score. If you want to go look at your individual scores, kind of you still can see those. So I want to leave student view. So the reason why, you should see, okay. So your Connect scores, like the actual scores, are out of a certain number of points, but because there was a different number of points in each one, each assignment is kind of weighted equally. So I kind of took the percentages and then kind of calculated the average there and put what your Connect grade should be down here as a separate item, right? So that's why, you can still look at your original scores on the Connect homeworks, but here's kind of what your current grade would be from that Connect section. All the Learn Smarts are worth the same. So here is kind of, calculates the average of your Learn Smarts and weights those by 10%. Your online quizzes, it takes the average of all those, weights it by 10%. Same thing for the Excel assignments. And then here, instead of having exam 1 and 2 show up for you now, I put those kind of in their own, in these old categories of like old exam scores. And then I use those exam scores to calculate what your lowest and highest score would be, right? So if it was, different people had their highest exam be from exam 1, some had an exam 2. And so kind of that's why I set this up to have just your current lowest and highest exam. Now I assume that they're going to be your best 2 grades in terms of the way I weighted them based off the syllabus. So 30 and 20%, kind of your worst exam only counting for 10%. So if you didn't do well on one of them and you do better on the final, then obviously like these would kind of get shifted down, right? But for right now, that's currently what your lowest and highest exam scores are, okay? So I wanted to point,
will change
once the final. And so next week, we'll go over it on Monday. I'll have a little like calculator tool to figure out what your grade would be if you got a 50 on the final or a 90 or, so I'll get I call it calculate your grade tool, and I'll get that posted next week, and we'll talk about it on Monday, or posted on Monday, and we'll talk about it.
On Canvas they have a feature like that.
Yeah, but with the weighting, yep, exactly. All right. So there's no questions about that or anything. We'll kind of get jumping into it. Okay. So last class, we're talking about the test statistic when we were looking at the difference between sample means, right? We also did, somewhere back here, confidence intervals for those situations as well, right? So today I'm going to show you how we would do this in Excel, and then at the end we'll kind of talk about what if we wanted to find the difference in population proportions. So I have this 2-population HT blank file, right? So if we start working off that, last class I kind of showed you how you can reference the data from the Midwest here. So this is like a sample of Midwest universities, their total undergraduate enrollment. I just looked at what's the average enrollment at these Midwest universities. So all that data is now over here. We have assumed true population variances. And for this data set, I have a collection of Southern universities, right, a sample. So I can find the sample mean for these Southern universities for this total undergraduate enrollment variable. I can get my sample size by using that count function. And now I've really got everything I need to build confidence intervals and do hypothesis testing, right? I've got each kind of population's sample mean, the population variance for each of these different 2 populations, and now my sample sizes, okay? So if I want to think about just what's the difference that I'm going to be building, say, a confidence interval around, well, I look at, let's do the Midwest kind of minus the South, right? That's going to be kind of our difference. We're saying the mean of the Midwest minus the mean of the South. Where does that true difference lie? Okay. So if we want to know where that true difference lies, we're going to look at the sample difference we found, right? And we're going to build our confidence interval around that. We don't have to put this here, but just as kind of a reference. So here's the difference that I found. Now I want to build a confidence interval around that. Okay? So the first thing that we're going to need to do, right? We have all these pieces of information, but we need to find these z-scores. Right? So the way we're going to do this in Excel, you can put it all into one cell, but we're going to kind of break it down so you can kind of see the intermediate. So here my z-value is going to be norm.s.inv. So this was the formula that we use when we know the areas we want in the tail. So if I'm looking at a confidence interval, I know alpha over 2 is on either side of my interval. Right? So alpha divided by 2 is on either side of my interval. However, I also have to remember that the positive and negative are already kind of built into my lower and upper bound equation. Oops. So I want to make sure that I'm not getting a negative value here. I just want the absolute value. Now, because alpha over 2, we're looking at that left side, it is going to be negative. So the way I can solve that is just use that ABS or that absolute value function. Okay. Once I do that, right, now I've got my z value for the 90% confidence level. Then I can drag this down, and it will update the alpha reference. And now I've got my 3 z values that I would need to build confidence intervals at these 3 different levels. So really at this point, it's just a matter of kind of using Excel as a calculator, right? And getting this entered into Excel. So let's say, what I first look for is the difference between the Midwest and the South sample mean. I then subtract that z value, that was the number of standard deviations I wanted to go away, right? Times the square root of times the standard deviation for the difference in these sample means, which is the square root of each group's population variance divided by that group's sample size. So we'll add those together for each of those 2 groups. And now we've got our lower bound equation entered in there. So it was really just a matter of getting this equation entered into Excel once we use Excel to find those z values. Okay? But if we try to copy this down, the only thing we want to change are the z values. We're going to keep using the same sample means, same population variance, same sample sizes. So we need to freeze everything except for that cell reference for the z value. So FN F4, or was it Command T on a Mac? Select, no, I have to select past the square root. There we go. FN F4, or if you don't have an FN key, just F4. Right, and freeze everything other than that z value reference. So now when I copy this down, I get my 3 lower bounds. I think probably the easiest way, you could type it again over here. But I can't just drag it over, right? If I drag it over, how do I get a negative upper bound? Well, it kind of moves over that cell reference. I'm no longer using that z value. So typically what I do, I get rid of this now, there we go. I just highlight this, hit Control C, or I believe it's probably Command C on a Mac, Control V, should get the exact same value. The only difference in our upper bound is the exact same equation, but we add that margin of error instead of subtracting it. Right? So just change that negative to a positive sign, and now we can copy this down, and we've got our lower and upper bounds. Right? So notice, as we want to say things with higher levels of confidence, the amount of values in our confidence interval expanded, right? The lower bound got lower, the upper bound got higher. So if we think about here, let's say the 99% level, right? What's the kind of true difference? Where could the true difference between Midwest and Southern schools be? So let's just draw this out. So 54 and about 7,700, okay? So we had this confidence interval. I think if we thought about the sample difference that we found, so the Midwest minus the South, it was around 3,900. I don't even know, I think 4. It was around 3,900. Kind of this upper bound was about 7,700, and I think the lower bound, that was 54. That's why I was thinking of 4. So with 99% certainty, I could say that the true difference between Midwest and Southern schools kind of mean undergraduate or mean enrollments is somewhere in this range. Well, these are all positive values. So with 99% certainty, I can say that that difference is greater than 0, which the only way this difference is greater than 0 is if the Midwest mean is higher. So with 99% certainty, I can say that this difference is 0, or that the mean enrollment for Midwest universities is greater than the mean enrollment for Southern universities. Okay? Which I wouldn't have known kind of going into this. But, you know, maybe I think, you know, if the size of the university drives different factors, well, now I'm pretty confident that there should be differences between the Midwest and the South. Right? So that was kind of our confidence intervals, right? How will we do hypothesis testing? So let's say we've got this set up. Let's do a right-tailed test here, okay? So I think the original file that was uploaded, this might have all been in text. So it might have looked something like this. I'm gonna edit that text so that I put the 0 in an actual cell here. And then for the alternative hypothesis, right next to that, I'm gonna put it's equal to that value. So just so it kind of looks like, you know, here's my, I don't know why it's formatted like that. That's goofy. So here's, oh, that's probably why. Because it does look a little bit better if I have it on this side, doesn't it? There we go. So there's my null and alternative hypothesis. We're always going to use this assumed true difference of 0, right? I'm going to show you what happens if we don't. Now, like I said, in the problems I give you or anything I would ever ask of you, I'm always going to use that assumed true difference of 0. So here we have a greater than sign in the alternative hypothesis, so a right-tailed test. First thing we're going to do is we're going to calculate our test statistic, okay? So that comes from, when we were talking about last class, this guy right here. So we'll take that sample difference, subtract the assumed true difference of 0, and then divide by, in the denominator, this represented the standard deviation of the differences in our sample means. Okay. So let's get this entered into Excel. So we took the Midwest minus the South. We then subtracted from that difference our assumed true value of 0, which we had over here in this cell. I'll then use parentheses again to make sure this kind of shows this is my numerator. Then what was in our denominator? What was the same thing that we used in our confidence interval, right? So here for a second, I'll get out of this so we can look here. When we use this in our confidence interval, the square root of each population variance over the sample size, this was the standard deviation for the difference in our sample means. So we're going to divide by the standard deviation for the difference in our sample means, which was just the square root of each group's population variance divided by its sample size. Oh, I hit the wrong button. Sorry. Oh, come on. I hate working on the laptop. So we'll then add the other group's population variance divided by its sample size, right? So that's our test statistic equation. So if we're assuming, if we have this kind of assumed true difference of 0, the fact that we found kind of a positive difference between our sample means, our test statistics should also be positive because this denominator simply represents a standard deviation. So hit enter, we get a test statistic of 2.6. So if I have a test statistic of 2.6, how would I then find the p-value? Well, think about what we're doing here. We have the difference in our sample means. Actually, I guess I could Midwest and the South, right? It should have been centered around whatever the assumed true difference was, which we said was 0. We found 3,908. What we're going to want to do for a right-tailed test is turn that into a test statistic and then find the area to the right of it, and that represents our p-value, right? The probability that we found sample evidence as far away from the assumed true value as we did, or anything further that went against the null. Okay? So we found this test statistic, I think it was like 2.6. We can use Excel. Now Excel is always going to give us the area to the left, so we'll have to remember whatever area Excel tells us to subtract it from 1 to get that area to the right. So what formula in Excel can we use? Well, if we know the area that we want in when we knew the area we wanted in the tail, and we wanted to find a z value that gave us that area in the tail, like when we did it with confidence intervals, we use that norm.s.inv. Now we know the z value, and we want the area to the right of it. Well, we can use that norm.s.dist function, tell it our test statistic, comma 1, and that will give us the area to the left. If we want the area to the right, what's the other thing that we have to do? Well, the area to the left of 2.6 is, I don't know, 0.9. The area to the right of 2.6 would be 1 minus that, right? Now, I've seen some confusion with past assignments and things. If you put a 0 in here, it doesn't give you the area to the right. It'd be really nice if it did. I wish that it did, but that's not what putting a 0 in here does. And so you have to use this, find the area to the left, subtract it from 1 to get the area to the right. Okay. So once we do that, we'll get our p-value. Okay. So what levels can I reject at? If I look at this p-value, could I reject when alpha is 0.1 or the 10% significance level? Well, I reject if the p-value is less than that. So yeah, it's quite a bit less. So I can reject at the 10% level. Is it less than 0.05? Yep. So I rejected the 5% level. Is it less than 0.01? Yep. So I can reject at the 1% level. I can reject at every single level here. Okay. Now I could have also found the critical values. Okay. So remember, kind of the critical values were the z values, right? Because we're dealing with sample means with known population variances. So the critical value is the z value that gives you kind of alpha in this right tail. Now, if alpha is 0.1, but I have to tell Excel the area to the left, when I put this into Excel, I'm actually going to want to put in the area to the left of the z value I want is 0.9. Okay? So the function that we have for that, when we know the area in the tail, and we want to get the z value that gives that to us, well, we already used that for confidence intervals. That was that norm.s.inv. We want alpha in the right tail, but this is the area in the left tail. So the area that we want in the left tail is actually 1 minus alpha, right? Not 0.1, but 1 minus 0.1 or 0.9. Okay. So we can do it that way, right? And that'll give us our kind of critical value. Or we can remember, well, if I were to just look up, say, use that norm.s.inv and just look up the z value that would give me alpha, because this is a symmetric distribution, it should be the same value but negative. So if I remember that, instead of doing 1 minus alpha, I could just simply say, well, I know I have a right-tailed test. I'll just take the absolute value of this, right? Okay. And now, you know, we just want to change the alpha, so we copy that down. Now we've got our critical values. Now, I say values. We only have one critical value. It's just 2 different ways that we could calculate it. So now I have my 3 critical values for these different alphas. What I would do is think about plotting those. Right? So I've got 1.28, 1.65 about, and what, approximately 2.3. My rejection region is anything more extreme or kind of even further to the right there. I would then plot that test statistic I found, which was what, 2.6. It's pretty clearly in all 3 of these rejection regions. Right? Any questions on that? Okay with that? So what about our rejection decisions? Well, I could set this up. I could do p-values or whatever. We could do the whole equals if, and then if the p-value is less than alpha, comma, I could put the word reject. If it's false, comma, put the word fail to reject. So we did a similar thing with one population examples. When I copy this down, I need to keep using the same p-value, but comparing it to different alphas. So I would put kind of dollar signs around that cell reference so that it freezes it. Right? Now I copy this down, and I rejected every single level. Okay? I could set it up using the critical values as well. If you look back at those one population examples, I'm sure we could figure that out. And I'm sure, so on Monday when I do this, I'll probably show you how you would set up this rejection decision using the if statement, using the critical value approach. But not to muddy this up too much, we'll just use the p-value approach on this one. So, this is, pretty interesting and kind of similar results is up here, with a confidence interval. Here with the confidence interval, we could have said with 99% certainty, it is a positive value, right? So if I try to test for whether or not it's 0, well, yeah, I should be rejecting the fact that it's less than or equal to 0. Because even doing my confidence intervals told me the true difference is somewhere in this range, right? So 0 is not in that range, so I'm going to be able to reject that. Right? Now, what happens if I start to get kind of higher values? Well, let's look at, it's similar to the confidence interval here. It's going to be a little bit different because it's a one-tailed test. So next week, we'll go through a two-tailed test example, and I'll show you how the confidence interval and the hypothesis test kind of exactly match up. But let's say, instead of testing for whether or not this true difference is 0, and what that is really saying is, I'll show you here in just a second. Let's see if this red shows up kind of good. So the mean for the Midwest minus the mean for the South, right? What we're saying is that difference greater than 0. What we're really saying is the Midwest mean greater than the South's mean. Okay, let's rearrange that. Well, what if I wanted to know, well, not only is it greater than, but is it greater than by more than 1,000 students, right? Well, now if I rearrange this, I'm actually saying is the difference greater than 1,000, right? So I could use these different values other than 0 to see how much higher the Midwest enrollment is than the South. So if I put 1,000 in here, everything updates. Well, I can't at the 99% level reject that the true difference could be 1,000 or lower, but I can reject it at the 90 and 95% levels, right? And then I could kind of keep going. Could I reject that's less than or equal to 2,000? I actually failed to reject at every level, just barely failed to reject, but I do fail to reject kind of 2,000 there at any of my conventional levels, right? So I don't have to use an assumed true difference of 0, but for all the examples that we're going to do, I'll always set it equal to 0, okay? Any questions on that? I'll get up here. We're good? Okay. All right. So let's go down here a little bit to comparing two population proportions. So just like we did with sample means, we could have two population proportion examples. Right? So we would take a sample from each population, they'll have their sample size, they each have their own sample proportion. They're also going to each have their own variance. Okay. Now, what the true variance should be, I think I have that down here, is what's the true population proportion for group 1? But the problem was all we have are estimates, right? So when we're thinking about confidence intervals and building confidence intervals, right, we need to know where is this difference between sample proportions centered around, and then what's the standard deviation for that difference in these sample proportions, okay? Well, it's very similar to what we did with sample means, so I'll kind of make this comparison. Right? So what we were doing with sample means was this, for confidence intervals. We're looking for the difference in sample means. That can be right in the glare. A little bit. Okay. So, let's see if I can get this glare to go down a little bit. So if you can't quite see this in the video or on Zoom, these are just the sample sizes for both groups. So N1 and N2. So we took the statistic that we're interested in. We then added and subtracted our upper and lower bound, used that Z value, multiplied it by the standard deviation of the difference in our sample means. So what we're going to do with proportions is pretty much the exact same thing. Give myself a little more room here. But now what I want to multiply by is the standard deviation between the difference in those sample proportions. Now, before we were using the variance, now we know the variance for these different populations should be this. I'll move out of the way in a second. Right, that's what they should be. But we can't observe the true population proportions, so we use the next best thing, which is we use our estimates to figure out what the variance is for those sample proportion distributions. Right? But it's very similar setup, just a little bit different than what we had with sample means. But all the same rules apply. I mean, we're using proportions. So same with one population examples. Anytime we see the word proportion, standard normal distribution. So same distribution, everything's going to be kind of the same steps, just a slightly different formula for that lower and upper bound. Okay? So here's our confidence interval formula. Let's work through the same steps. Identify the piece of information you need, find that z-score, plug everything in. Right? It's the same kind of steps. So let's work through an example with some values. So let's say I'm looking for the difference between, what's the 99% confidence interval for the difference between 2011 and 2010 for reports of favoring healthcare coverage, right? So in 2011, 84% were in favor of ensuring healthcare coverage for everyone, sample size of 607. 2010, 82% with a sample size of 600. So what's the true difference in attitudes towards ensuring healthcare coverage for everyone between 2011 and 2010? So we'll use remember, we always use the newest year, the latest data kind of first. We're thinking about how things change over time. So group one kind of we'll be sampling from would be 0.84 as the sample proportion, and group two has a sample proportion of 0.82. So first of all, what's the difference we find in these sample proportions? So 0.84 minus 0.82, that's a positive 0.02. Well, that's not even in the range of values for C. So C doesn't make any sense here because the actual sample proportion, the difference we found in the sample proportions isn't even in that interval, right? And we know that our confidence interval has to be centered around it, right? So we'll identify the pieces of information that we need from the problem, 2 sample proportions, 2 sample sizes. We then have to figure out what alpha is. Well, kind of sneak peek, I gave you 0.01, but the reason why is because at the 99% confidence interval, right, alpha is just the area outside the interval in decimal form, so 0.01. We then have to divide that by 2 and find the z value that gives us 0.01 divided by 2 on each side. So how did I find that? We can use the standard normal or the z-table, and we can use the standard normal z-table or the t-table, because I think, I had a student ask me why do you show us how to do it with the z-table? It's easier than the t. I agree, I think it is, because once you know that you want 0.005, right, that was alpha divided by 2, 0.01 divided by 2, that's the area you want in the tails. If you just go to the last row of the student t-table, these are the standard normal values. So 2.576. Right? So once I have that, right? Once I have that z value, now it's just a matter of getting everything plugged into that lower and upper bound equation. Once you get your numbers, it's just a matter of getting comfortable using your calculator, right, to solve these. Okay? So once again, I think I mentioned this with one population example. Sometimes it's easier to work backwards here in terms of like if you're doing this on a calculator, but it's really, I think, just getting some practice. So with the homework, the Connect homework, and next week we'll probably do a few more kind of online quizzes. I won't do them this weekend. I'll give you a break. But making sure you can replicate these results, right? So we get a confidence interval from negative 0.03 to 0.07, right? So here, what can we actually kind of say? So it was negative 0.036, 0.76. So now the true difference could be positive, which if we're trying to predict where this difference between 2011 and 2010 is, this true difference, here I can actually, let me just erase this. So we're looking at the this confidence interval for where that true difference in the proportion of people who favored healthcare, ensuring healthcare coverage for everyone from 2011, so 2011 and 2010, it could be a positive value, which would mean if it's positive, the only way that's possible is if 2011 proportion was higher. So it could be that 2011, more people favored it, but it could have been, the true difference could be negative, which means that 2010 would have to be higher. And it could also be 0, which the only way the difference could be 0 is if those proportions are actually equal to each other. Right? So with this confidence interval, we really can't make a lot of statements. There's nothing like very interesting that we can say because it includes positive, negative values as well as 0. Anytime it crosses over 0, just can't really, it's not as useful. Right? So, where are we at on time? So instead of kind of going through this one, I think what I'm going to do here is, it's just an additional example. If you want to kind of work on it on your own, it's really the exact same setup. It's just we're looking at a different question, which is, do they have unfavorable views of the Affordable Health Care Act? 51% and 48%, so 0.51 and 0.48 are going to be our two sample proportions. It was the same survey, so they're the same sample sizes. I want a 99% confidence interval. What's the Z value they want to use be? Well, what were we doing before? 99% confidence interval. So, right, alpha would be 0.01. Here, oops, alpha would be 0.01. Well, we're still using the standard normal distribution, so we're going to find that same Z score of like 2.576. You know, and from there, it's just a matter of plugging everything into our equations there. So, if you want to, you know, like I said, some good practice to make sure you can replicate these values just to start to get comfortable to enter these into your calculator. So I use this example because I thought it was kind of interesting. This was the same people, and like a large majority of them favored ensuring healthcare coverage for everyone. But when asked if they supported an act that pretty much that was its main goal, it fell to like 50%. So this kind of gives a nice highlight of, depending if you ask someone, you know, something in a certain way, you might elicit some very different responses, right? Some people knew I'm not supposed to like the Affordable Health Care Act, but when you actually ask them, well, do you like the thing that it's doing? Yeah, I'm all about that.
Or like the video, one of the late night talk show hosts they put out, like, do you like Obamacare or the Affordable Care Act?
Yeah. It's all about how you phrase things, right? So it's very interesting, like, there's such a significant difference here, right? 80% down all the way down to 50. Yeah. But, so that was kind of an interesting example. That's why I use those. But yeah, you can kind of make sure you can go through and replicate these values. It really is just a matter of getting comfortable using your calculator. All right, so a little bit different with proportions is going to be how we do hypothesis testing. All the same steps apply, right? But we're going to have a slight issue. So I'll show you the test statistic first, and then I'll explain kind of why it is what it is. So kind of notice here, you know, looks very similar to the sample mean. When we're looking at difference in sample means, I just look at the difference in sample proportions now. I have my assumed true difference, which I'll subtract from that. But now this denominator, which remember, the denominator we had before, so when we're looking at the difference in sample means, we had the variances over the sample sizes. This was a standard deviation of the difference in those sample means. Well, now we have this goofy guy when we're looking at the difference in proportions in our denominator, which is p bar times 1 minus p bar times 1 over n1 plus 1 over n2. Right? Well, this still, like this guy here in the denominator, still represents a standard deviation. And in fact, it represents the standard deviation in the statistic that we're interested in. The only reason why it's a little bit different than like what we're using the confidence interval is because if we think about what we're doing, when we have this assumed true difference for what the sample proportions are, if we go back to the confidence interval equation real quick, the general form of it, right? Oops. God bless it. All right, there we go. When we were trying to calculate what the variance would be for these different sample proportions, we were using these estimates because we didn't know what the true population proportion was. Well, now when we go down here to the test statistic, oops, the reason why it has to be a little bit different is because before, what we were doing with one population examples, when we were dealing with proportions, this is a kind of a reminder, we would take sample proportion minus the assumed true proportion divided by this. That was our one population example. So what we were using in that denominator was this assumed true proportion. Well, the problem is we have an assumed true difference now. So if we assume the difference is equal to 0, it could be that, kind of think about this as like, it could be, I'm going to run out of room here. So if I think about this assumed true difference, I could write it as like the assumed true difference from group 1 minus the assumed true difference from group 2. But that's not what I'm actually doing, right? I don't have an assumed true difference for each one of these. So it could be that to get this assumed true difference of 0, these both could be 0.8 or they both could be 0.4. So I don't actually have an assumed true value for the proportions. I only have an assumed true value for the difference. So because of that, I have to calculate the standard deviation a little bit differently to ensure that these these are actually z values when I'm calculating the test statistic. Okay? So kind of creates a little bit of a headache. It's one more step, but I first have to calculate this p bar, which you can kind of think about it as kind of taking the kind of weighted average here between the two proportions. But I'll plug those in, plug in my sample size and my sample proportions, plug in p bar, plug in my sample sizes, sample proportions, the assumed true difference is 0, and now I've got my test statistic. Right? So it's kind of one more additional step. I mean, technically you could write out p bar in this denominator and have this really, really big denominator, but it's easier to just kind of first calculate that p bar and then kind of plug that in. Okay? And like I said, really what it is a weighted mean, right? I'm taking each proportion, multiplying it by its sample size, and dividing by kind of total observations, I guess, I have between both these samples. Okay. So the only, once I know that this is my test statistic equation, everything else is exactly the same as what we were doing with two sample mean differences. So all the steps, exactly the same. It's the exact same steps we had before. So let's work through an example. So prior to the election, I had kind of this idea of like, well, actually look at some of this polling data and see like whether or not it would predict the outcome or not. So I grabbed this Rasmussen phone poll data of 1,500 likely voters. Had 49% were planning to vote for Biden, 47 planning to vote for Trump. So if I wanted to test the proposition that Biden will receive more votes than Trump in the upcoming election, what would my null alternative hypothesis be? Right? So if I want to know whether or not Biden is going to get a higher number of votes than Trump, what I'm really saying there is the proportion of votes that are going to be coming in for Biden greater than the proportion of votes that are coming in for Trump. So if I rearrange this equation a little bit and I'm thinking about my differences, the difference between Biden and Trump votes, I'm really saying is that difference greater than 0. So that's going to be what I'm testing for. So that becomes my alternative hypothesis. I assume the exact opposite is true, which is that that difference is less than or equal to 0. And that's my null alternative hypothesis. So here I have what type of tailed test? Greater than sign of the alternative hypothesis. So a right-tailed test. So I have a right-tailed test. First thing I'm going to do is find my critical value. All right, so I'm going to do a critical value at the 1% level. So my alpha here is 0.01, and I have a right-tailed test. So what that looks like visually is I've got this right-tailed test, I know that I'm using that standard normal distribution because I'm dealing with a proportion. I want the critical value that gives me that alpha of 0.01 in that right tail. Right? So when I kind of look this up on the table, I would actually want 0.99 to the left. So one thing that's kind of nice is we actually did that already over here in Excel. Right? We had a right-tailed test. Yeah, it was for difference in sample means, but it doesn't matter. If you're using the standard normal distribution, anytime you look up alpha, you're going to find the same z-value. So 2.326, right? Or if we use that student t table, look up the alpha we wanted, 0.01, all the way down in the last row, that's the standard normal value, 2.326. So we get 2.326 is going to be our critical value, right? What about the test statistic? Okay. So first of all, we could plot our critical value here. So 2.326, get rid of this. And think about our rejection region then is anything to the right for a right-tailed test. So then calculating our test statistic, right? It's just a matter of, we know what equation we need to use now. We've got kind of our critical value here, and ignore that divided by 2. I think I copy and pasted this from the confidence interval slide and I forgot to change that. So here's my test statistic equation. So I first calculate P bar, where I plug in my sample sizes of 1,500, my sample proportions of 0.49 and 0.47. I get this average kind of P bar of 0.48. And this one kind of is highlights that it is finding kind of this weighted average between the two because we had equal sample sizes here. So I then plug 0.48 in as P bar, 1 minus 0.48 is 0.452. My assumed true difference is 0, so that kind of goes away. And then it's just a matter of making sure we can get this entered into our calculator. So we get a z kind of value of 1.097. Right? So if I think about this, could I reject the null at the 99% level? Well, it wasn't 0. I'm going to do this a little bit out of scale here. All right, so 1.09, right? That was my test statistic or my z statistic. Clearly not in my rejection region here, right? So I failed to reject. Now remember, my null was that this difference was less than or equal to 0. So if I write this out in a slightly different way, it was that kind of proportion for Biden minus the proportion for Trump was less than or equal to 0. Right? So I'm failing to reject that difference could in fact be less than 0, which would mean Biden's getting fewer votes, right? So that could have been the case that I didn't find strong enough evidence where I could reject that Biden could potentially not win the popular vote. Now, obviously, we know that in practice he did, which means I made a type 2 error, right? I failed to reject the null when in fact I should have. So, but if we want to take this a step further, well, what if I think about take that test statistic and find the p-value, right? So I want the area to the right there. So I'll look up 1.09, and for that, I'll need to use my standard normal tables. So 1.09, the area to the left is 0.8621. So if the area to the left, 0.8621, the area to the right, or my p-value, would be 1 minus that, so 0.1379. However, I only rejected the p-value is less than alpha. Is this going to be less than an alpha of 0.1? Not quite. So even at the 90% level, I failed to reject the null, right? Now, the interesting thing is, if I wanted to give myself a little leniency, what if my alpha was 0.15? Well, now I could reject the null with 85% confidence, which isn't that low, right? So, So even though we didn't find sample evidence that went against the null kind of at these higher levels, it still was pretty strong evidence that went against that assumption that Biden was going to get kind of fewer votes than Trump in the popular vote. Okay? So that was kind of a pretty relevant, interesting example there. don't believe I had kind of a slide there for finding the p-value, right? I just kind of used that critical value approach, but we could have done that p-value approach as well. And kind of the nice thing about the p-value approach relative to the critical value is I can kind of really look at this and say, well, look, I can't reject the null at kind of these three conventional levels, but I can reject it with like 86% confidence here, right? A pretty high level of confidence. That p-value isn't really, really large, right? Any questions over any of that? Okay. I think we'll actually stop there for today. I want to go through this second example, start class Monday with it, and then we'll kind of do some difference in proportion example in Excel, and then we'll move on to examples where we don't know kind of the sample variance. So you should have a pretty good amount to get through, like about 2/3, enough knowledge to get about 2/3 of that Connect assignment done. And then I'll post the next Excel assignment. And we haven't went over any specific examples that will be on it, but based off what we did today and kind of the discussion we had about proportions, I'm sure you could figure out how to work on parts of it. But I'll get it posted early. I'll post it today, even though probably you won't be able to really start working a lot on that Excel assignment until next week. But the Connect assignment, you should be able to make some headway with, right? And I think the due date was showing up a little earlier than I had wanted. So both those assignments, and I'll post an announcement, but both of them will be due on December 4th. So not until that Friday after Thanksgiving. So you'll have time to kind of enjoy the break there and everything. Okay. All right. That does it for me. I will see you guys on Monday.